It's okay. Okay. Welcome to technically the last session. The only session we have after this is, the lecture. I would request Professor Chandan Dasgupta of the Physics Department to take over as the chair. Oh, sorry. One quick announcement. Some of the people are requesting a group photograph, which is a good idea. Probably should have been done yesterday, but if people are here, we should still have it. So if you can assemble outside the physics department, just at the entrance, after this session, at the beginning of the tea, I'll tell the photographer to take a few pictures.
Okay, so good afternoon and welcome back for the post-lunch session of this third day of the conference. We have two talks in this session. The first talk is by Professor Brijesh Kumar from the Jawaharlal Nehru University in New Delhi, and he will speak on quantum Ising dynamics in the Rabi lattice model. Brijesh.
Okay. Good afternoon, friends. And let me begin by thanking Arindam and Krishnendu for giving me this opportunity to talk about my very recent small calculations. And so here it is, quantum Ising dynamics in the Rabi lattice models and the search for Majorana fermions. That is one possible connection to the theme of the talk, including the Rabi lattice itself. And this is a recent manuscript which is on the archive. Some of you who may be interested in it can take a look. I got interested into this subject of lattice models of quantum cavities basically by looking at these two papers which appeared sometime, 2006, back to back in Nature Volume 2. And they are basic, and these are theoretical papers. And their basic motivation was to study the quantum dynamics or quantum phase transitions of lattice models of quantum cavities. And this was the prized conclusion of that paper, or these two papers in collective sense, that a lattice of such cavity QED systems exhibits a phase diagram which is basically Mott insulator superfluid kind of phase diagram, as we know for the celebrated Bose-Hubbard model. So this was basically the highlight, that you have another quantum emulator or simulator in the business apart from the standard cold atom things which they have been doing for so long. And just to recap a bit, we all know what Bose-Hubbard model is. Subrata talked about this in the morning. It's basically some on-site repulsion for putting more than two bosonic particles on the same site, and this is the hopping. And you have basically, if you vary the chemical potential, which means when you populate the lattice with more and more I'm sorry, I work with electrons more than bosons, so I'm kind of mixing my bosons with electrons, but here we are strictly talking about bosons. Then for commensurate fillings, such as one particle per site or two particles per site, we have transition as a function of T, which is hopping, that you can be in Mott insulating phase or in the superfluid phase. And this phase diagram here is not for Bose-Hubbard model, but the similarity cannot be missed. So, but I'll not be talking about Bose-Hubbard model. I'll be talking about cavity QED systems, in particular the lattice models. And one good thing about talking in the last session is that I don't have to introduce too much. And a lot of beautiful things have been taught to us during the school, particularly by Professor Steve Girvin. So I'll refer you to that introduction. But I'll still introduce the problem that I'm doing, so I need something to show. A cavity QED system refers to a matter radiation problem inside a high Q resonator with quantized electromagnetic radiation and an atom. And the minimal problem that one is concerned about in such a setting is basically an effective two-level atom. Again, there have been so many instances of where and how the two-levelness can arise or be possibly realized in various situations. So I'll not talk about specific physical realization, but I'm just saying let there be a two-level atom. And again, even though there are many different allowed modes, which means omega k's and ak's, but I will only pick up one, which is, let's say, coupled to this particular atom. So this may be the most dominant resonant mode of the cavity, and this is the frequency which is close to that. So, and we all know that any two-level system, be it atom or anything else, is basically a spin-half object, and that's why I'm using these operators sigmas, which we typically use to discuss spin-half. So a two-level atom is synonymous with spin-half. So if you could as well be talking about a spin boson problem or a resonance problem, and you could use basically the same description. Yeah? No, this is just a constant energy, but this is, yeah. So epsilon bar is just some constant energy. Then, of course, we have to also take into account the minimal interaction between atom and radiation. And this is a very standard chapter in any standard quantum optics book, how to derive the minimal interaction between matter and radiation. And at least from the quantum optical perspective, where the wavelength of light is much longer than the size of the atom, we can make what is called long wavelength approximation, and the simplest form of the interaction is nothing but a dipole interaction. So P dot E, where P is the atomic dipole and E is the electromagnetic, the electric field, let us say, of the mode that you are exciting in a cavity. And in the language, in the notation that I developed or introduced in the last transparency, sigma x is nothing but the atomic dipole operator. And A dagger plus A is nothing but the electric field, as we learned in the lectures by Steve Griffin. This is nothing but the coordinate, if you wish, of the oscillator. So the minimal interacting problem in a cavity is, in a single cavity, is a photon and an atom and a dipole interaction. This is all physical, I mean. And in fact, this is often termed as Rabi model in the honor of Rabi, who basically developed such, studied the resonance problem, the precession of spin halves in the magnetic fields within this framework, basically. For our purpose, we will also need to note that this model has certain symmetry properties, and in fact it has very simple symmetry properties. There is nothing much which is conserved except the parity, and these terms will become clear a little sooner as we go along, but let me just tell you that this is the rule book. Parity is plus if the polar electron number is even, and parity is minus if polar electron number is odd. Then came Jaynes and Cummings. See, let me also tell you a very interesting fact about this model. Even though it looks very simple, its simplicity is deceptive, in the sense that it cannot be solved. If you want to solve the eigenvalue problem for this problem, you cannot do it. Nobody has been able to do so far, even though people have, as recently as 2011, tried to systematically show some aspects of integrability and so on, but that doesn't guarantee that you have solved the eigenvalue problem. So this problem is very difficult in that sense, because the symmetry is minimal and the matrices involved are basically infinite by infinite, and there is no obvious way to solve them. Now, sometime in the 60s, Jaynes and Cummings were basically interested in this problem, and they realized that, well, if you ignore this term for whatever reason, and that reason is called rotating wave approximation, or that approximation is called rotating wave approximation, the reason they give is that these terms are faster. If you just think in terms of time dynamics, the frequencies associated with these guys will be basically omega plus epsilon, whereas the frequencies associated with this term will be omega minus epsilon. So if you are sufficiently close to the resonance, you can safely say, well, this is the term which is going to contribute on a longer time scale, and I can safely ignore the fast term. And this is called rotating wave approximation. So along came the Jaynes-Cummings approximated version of the Rabi problem, and this is fortunately soluble. But this approximation is also very drastic in the sense that it changes the nature of the problem itself. The symmetry of this problem is basically polar electron number is conserved, which means the number of photons plus the number of excitations in the system is conserved quantity. And that makes a lot of difference, which is not the case in the full Rabi problem. In fact, that's right. So, I mean, there have been suggestions of actually trying to realize these problems, the Rabi problems, within a framework. Even though you start with the JC model, people have suggested schemes whereby applying the drive fields, you can actually try to convert it into an effective Rabi problem. So people are very interested in trying to simulate or realize such model problems in a much more controlled manner. So let me come to the main objective of my work, which is to investigate the quantum dynamics of arrays of such quantum cavities or cavity QED systems. So when I say let us form a lattice of such quantum cavities, what I mean is that the atom stays put inside each cavity. So atom is not hopping around, but there is a finite tunneling amplitude for the photon to leak out into the next one. So when I say form a lattice of such cavity QED systems, it basically means you allow for photon hopping between neighboring or further neighboring cavities. So naturally you can have... No, this is real photon. It's like, electron tunneling from one orbital to another. It's exactly the same way. No, this is all real. So the T is not virtual transition. It's basically a real, it's like saying connecting the two microwave cavities with a cable. It's basically that. So one could study the full Rabi lattice, or one could study the Jaynes-Cummings lattice, which means each cavity is either of the JC type or of the Rabi type. What had been studied in those papers that I mentioned in the beginning were the JC quantum cavity lattices. For some reason, maybe because historically Jaynes-Cummings problem became widely used and of course meaningfully made approximations. So this is the most sought after model so far. And if you do a very simple-minded calculation pioneered by people here, basically do a Curie-wise decoupling of the T term here, you will generate such a phase diagram. So any of you can basically do this, generate this phase diagram and get a nature physics, but you have to be on the right time. Yeah.
The shape of the phase diagram seems to be very different from a standard crossover. So is there a difference in the Hamiltonian that you have?
Oh, yes. I mean, see, when I say that the similarity is in the sense that there is a conserved quantum number, which is number of excitations, in this case polytons, and there is a superfluid to Mott insulating transition. But the nature of Hamiltonian is of course different, because hopping is same as Bose-Hubbard, but this HJC is HJC. So you don't have U here as such, but you have atom acts like a nonlinear medium which generates an effective U. See, if you solve the Jaynes-Cummings problem exactly, then for a given quantum number n, which is the photon number, let us say, the energy eigenvalues will roughly look like something like this, plus gamma square n square plus omega minus. I mean, I'm not bothered about the factors here, but you can see, so effectively it's like this. If let us say we are at resonance, so there is a nonlinearity. And this is what Professor Given alluded to, that if there is a means of generating, making these level spacing uneven, then you have basically a interacting problem. Yeah. Well, the superfluid here basically means this, which means spontaneous electric fields, basically. No, so this would be spontaneously generated. So either you have atom and photon forming a polariton state and doing nothing, which means hopping is ineffective, that is this phase, or you have basically photons condensing, which basically means you have a spontaneous electric field, because having a non-zero expectation for A basically means having a spontaneous electric field. So superfluid here means that. Yes. Well, I mean, sorry?
Many Mott lobes.
That's right. These are Mott lobes. But if you want to, you want to ask me why they are little wiggles, or? No, of course. You can derive this boundary exactly the way you can derive the phase boundary for Bose-Hubbard model by doing so basically decouple this term by using this mean field, and do a small, suppose this is your order parameter. So do a small A bar calculation and compute the phase boundary.
This is the mean field phase diagram corresponding to the Hamilton.
But let me, yeah,
That's all it is.
that's all it is. But I'm saying this has been also checked by various other techniques, including DMRG, etc. And the actual shape may, the numbers may be different, but the overall topology of the phase diagram is same. So you have, yeah, that's all. That's all.
So I had a question. Has anybody, and I don't follow this field at all, has anybody looked at, because for Bose-Hubbard model, people have looked at every possible variance, longer range hopping, multi-band lattice, all those things. I myself have done it. So have people done all those variants here? Like, do they know if there is a super solid phase here?
I do not know, but it seems like there are lots of people interested in studying it. People have.
There are many papers.
There are many papers. I have not been very systematic about citing them, but if you do.
I did not, I'm not interested.
No, I understand. But what I mean is that I'm not here particularly interested in giving the survey of this field, but this is just a motivation. This is not the. But there is a lot more literature about this than the Rabi problem, which I am going to investigate. Yeah. Yeah. So let me go ahead then. Okay. So let me now come to the Rabi lattice, which is what interested me. Well, basically, I wanted to do something which others were not doing, because I tried to see if somebody has looked at the full physical problem, which means without. See, there is a reason why I wanted to not drop the fast terms. The reason is following. If you go back and look at this phase diagram, this is in units of omega by gamma, where gamma is the atom-photon coupling. All these Mott phenomena is appearing for stronger and stronger gamma. Because if gamma is strong, then you are basically going down. So this going downwards means strong atom-photon coupling. Now, if you really have very neat and clean system, suppose no incoherent losses and so on, and you have very strong atom-photon interaction, then there is no reason why to drop such fast rotating terms, because they are after all there. I mean, we made approximation for some convenience sake. It's not as if you throw it out. And therefore, I wanted to keep those terms and see in what manner the phase diagram would change. Yeah.
This fast term and this slow term, can we look at it in a form of an approximation kind of?
Well, in some sense, this is what it is. It's a dynamical way in which you argue that there are some terms which are very fast in time scales, or non-energy conserving terms which will be short-lived, and the others will be.
So instead of dropping the first fast term, can I solve with the slow term static and solve for the fast term and then plug?
In principle, yes, because there is a particular symmetry in which you can convert sigma pluses into sigma minuses, and the fast term becomes slow and slow terms become fast. But that's like redefining your atomic states. But that doesn't necessarily mean that you have done something new, because you are still going to drop one of them. So what I want to do is drop nothing, keep everything, and see what is the answer. Yeah.
You say the Jaynes-Cummings lattice model is exactly solvable?
No, I'm saying that first of all, Jaynes-Cummings cavity, single cavity is exactly solvable. The lattice has number conservation, but you can't solve it exactly in the sense that, well, for smaller sectors you can, but as you increase the number of polar electrons in your system, the matrices become bigger and bigger, and they are not simple tight bindings. Okay. So yeah, that's the correct statement. So that is basically the reason why I wanted to study this. And while I was putting my thoughts together, these two groups also started studying this problem, and fortunately they did not do what I did, so I still have a chance to talk about it. So, but still, let me say what they did. Well, these two people computed the phase diagram in some approximation and did realize that the nature of the phase diagram will be different, because this model has discrete symmetry as opposed to the full Rabi lattice problem. I mean, the approximate Rabi lattice problem, which has particle number conservation, just like Bose problem. And the Shiro group, well, Shiro et al., I mean, Shiro was, I think, is a postdoc in Princeton somewhere. And they arrived at basically a conclusion which is partially similar to mine, that there will be an effective dynamics in the problem, which is that of the quantum Ising type. but they arrive at that conclusion through a method which is pretty different from mine. But what I have done is basically made a somewhat systematic and rigorous statement that in the strong atom-photon coupling limit, the Rabi lattice model will basically become quantumizing model. So it's a much more rigorous and systematic statement. And then, of course, if you have quantumizing problem in hand, you have Majoranas for free, at least in principle. So I'll basically present some observations which I could figure out in already existing literature on quantumizing model, that there is a parameter independent way of trying to detect Majorana modes in this problem. Okay, yeah. So let us go back and look at the single cavity again. As I said, this is a symmetry of the problem. Now, this is not obvious from the Hamiltonian unless you know why this is a symmetry. But can we make it a little more explicit? And the answer is yes. I could figure out a simple transformation. If you do this transformation, basically you achieve this. This transformation eats up sigma x. So you can see A becomes sigma x A. Physically, this means that the photon field now carries the Z2 phase of the dipole.
Sorry, what is chi in that first, in your parity definition?
And chi is minus 1 to the power n. I had defined it earlier. So so chi is the parity operator for bosonic subsystem, if you wish. So this unity transformation is basically trying to eat up the phase, the Z2 phase of the atomic dipole. So now in the transformed version, interaction basically becomes a displacement. However, the sigma z gets modified, and you can notice now parity becomes sigma z. And this problem, the single cavity problem, basically is diagonal in your sigma z variable or the parity variable. So in this new basis, if you wish, the parity is somewhat more manifest. Okay, fine. What about the lattice? If you do the same thing now for the entire lattice, the dipoles which had disappeared earlier actually reappear again, but through hopping. So let us look at these salient features or important features of this transformed Hamiltonian, the Rabi lattice problem. The atom-photon interaction has been simplified into a static phonon field, and the local parity fluctuations which happen through T, and we know it if we systematically look at the problem, become more manifest, that the atomic dipoles via the hopping make the sigma z fluctuate. Because now you remember, in the H1 at the level of transformed problem, sigma z is my parity. Okay. So the only thing you have in the problem now is not even the local symmetry, the global parity. Very highly constrained problem. Not much to do for the system. I mean, for me, there is a lot of thing to do, basically. So, so let us see if there is a limiting case in which we can appreciate what is going to happen. Now, this problem manifestly has a displacement field, and it's not self-consistent. Gamma is a fixed number, which means you are biasing these photons to develop a static field, which means A dagger expectation will always be non-zero. Now, if that is the case, why not let that expectation be very large, which will be proportional to gamma? So, how will you first of all go into that basis which will talk about the static field plus the fluctuation? Well, all you have to do is the displacement. This is simple operator. Everybody knows it from oscillator problem in quantum mechanics. And the effect is to displace the photon. Physically, it means that now you are talking about fluctuations on top of the static field, which is gamma by omega. And of course, this chi, the parity, the photon parity becomes a little more complicated. This is very interesting because this term will have an effect very similar to Ham suppressions or these Frank-Condon factors in the vibronic problems. So for the full problem, we have a rather messy looking object. I mean, after having done the displacement or going into the displaced basis. So as I said, since anyway there is going to be a static field, let me take the static field term to be dominant. So how do you achieve that? You achieve that by making gamma stronger and stronger. And if you do that, what do you get? Well, what do you basically mean by saying let us look at the gamma large limit? You keep the static displacement field and ignore the photon fluctuations to the leading order. So you just don't care about the photons which are there, because your static field is too large to worry about the little fluctuations. And since we are interested in the quantum phase diagrams and so on, just take the photon state to be 0 basically. That's what it means. What does it mean then? It means, and this is a limit, I'm not doing any, this is not effective business, this is all exact. So you start from Rabi Hamiltonian, and you systematically arrive at a conclusion that in the limit when gamma is very, very strong, the largest energy scale in the problem, then you are left with just this. So the strong coupling quantum dynamics of the problem is governed by nothing but quantum Ising model. So this is the limiting Hamiltonian starting with the Rabi problem. And this is it. There is nothing else which the system can do. Of course, if you have not so large gamma, then it means you have photon fluctuations which will renormalize these behaviors and so on. All of that is of course accepted. But let me look at the simplified limit which we have by good chance hit upon. And this is true for any lattice. So as I said, this transformation business did not care about on which lattice you set. So no matter what lattice you form, this gives you a lot of freedom. You could as well form honeycomb lattice, you could as well form Kagome lattice, and you can study all kinds of lattices, but all for the quantumizing case. The notable features of this limiting problem are, well, of course, you have a Ising interaction, which is, because I am taking T to be positive, is ferromagnetic, or ferroelectric rather, because I am using the language of atomic dipoles and so on. And this is the transverse field. And now you see this exponential factor. This is coming about because of this term. So when I ignore the photon fluctuations basically and putting the photon number to 0, this factor will become 1, and all you are left with is a yes. This one. No, but this is just a static displacement energy. It's like choosing a new 0. That's right. But it is not in that sense. This is some large negative energy sitting at the background, and you don't care about it. You are just looking at the quantum dynamics on top of it. So this is a very interesting factor arising because of basically you are working in a displaced basis. Okay, few more things. First of all, even though to begin with we had 4 parameters in the problem, we had epsilon, we had omega, we had gamma and T, and in units of any one of them. So I am taking gamma to be my unit of the problems. So we have 3 independent parameters. But in this limiting case, there is only one effective parameter which is going to govern so there is a universal character to the problem. And as you will see, the useful phase space would be T by epsilon and omega by gamma. And this is where you will see a lot of universal features coming together. That's right. What else do we expect from based on this very simple limiting Hamiltonian? Well, if J is bigger than H, then you have ferroelectric phase because sigma axis, the atomic dipoles would like to polarize spontaneously. This is analog of what people call superfluid phase in the Jaynes-Cummings problem. The reason why I am not calling it superfluid phase, because first of all it says ferroelectric phase, my physical variable is atomic dipole. Secondly, even if I were to talk in terms of superfluid of bosons, which means photons here, then this expectation is roughly P times gamma by omega. Now gamma by omega is large amplitude which is always there. So the phase transition is governed by this discrete P. And in other words, what I'm saying is, even though there is this non-zero expectation, it doesn't have theta freedom. It's a discrete variable. Either you are on the plus or minus. That's all. So it's because superfluidity means you have a continuous U1 symmetry breaking. Your order parameter must be complex number. There should be a continuous theta freedom. But here there is no continuous theta freedom. You just have either plus P or minus P. So it's analogous in the sense that A bar is non-zero, but it's not strictly speaking superfluid phase. Then if you have J lesser than H, then of course you expect no spontaneous order, this term will win, and you have paraelectric phase. So these are your physical, in fact these guys tell you what to measure. You measure spontaneous polarization of such a lattice if you are able to achieve strong couplings, or even if you are on a moderate coupling range, and see whether the spontaneous polarization is developing or not, and that's your physical measurement. And you can then check what theory tells you. Well, so here is a plot which basically, so we did basically DMRG calculations just to support all the systematic arguments that I had used to build up this description. So these data points are DMRG on 1D chain, and the black line is basically analytical expression, which is known because fortunately one good thing about quantumizing problem is that we know so many things about this problem. It's a very highly studied problem. You just have to borrow results and and basically do very minimal effort if you like. So this is a very well-known result derived by Feuchte in 70s, and this exponent is exactly like 2D Ising model thermodynamic phase transition because they are in the same universality class, and they match pretty well. Okay, what else? You can compute phase diagram. So because now we know exactly what the parameter is, lambda is the parameter which governs the phase diagram. This is how you can even compute the exact limiting phase boundary, and this black curve is the exact phase boundary. So let me see. Okay, okay, fine. So this black curve is the analytical answer. The data points are generated for different values of epsilon because that is the free parameter in my problem if you wish, because remember I had three parameters in principle: omega by gamma, T by gamma, and epsilon by gamma. So this is omega by gamma axis, and I explained to you earlier that T by epsilon will lead to some interesting features. So I'm using T by epsilon as my other axis, so the remaining parameter is epsilon by gamma. So of course if your omega is on the higher side or your epsilon is slightly bigger, whatever, these curves will depend on epsilon, but eventually they are all falling onto this same universal curve. And this is the reason why I had plotted them as T by epsilon and not as T by gamma. So there is this is a very interesting plot that you may, in fact this is a comment I want to make here now, that in the strong coupling limit the epsilon becomes meaningless, which means whether you are near resonance or far resonance doesn't matter because of this suppression e to the epsilon e to the minus 2 gamma square by gamma omega square by gamma square factor. Okay, and then well, so I think let me not talk about improvised version, but that it simply means you take the effect of band structure into account, and that can be systematically done. And you can see that these guys, the dotted lines here, which are matching reasonably well with the numerical ones, are the improvised version of the same formula. So this is a way to incorporate the effect of P, the band structure. Yes, I'm almost there. I have 2 or 3 more transparencies. So now I come to the connection with Majorana fermions. We all know that the quantumizing model is nothing but the P-wave superconductor in a suitably chosen representation. And this is what had been discussed earlier in the school. This cartoon would be very helpful in the sense that you can imagine each dipole moment sigma x to be made out of 2 little poles, if you like, the blue and the red. And just consider 2 simplified limiting cases. In one case there is no J, in other case there is no H. If there is no J, then this is a local term. Each dipole is sitting wherever it is sitting, and the 2 ends of the dipole are tied to each other. If you look at the other limit, which is no H but only J, then you have a funny situation. Even though originally you had started with these 2 poles, but the binding is between the poles, opposite poles of the neighboring guys. So this is basically 1 and 2 paired up to form a dipole, 2 and 3 paired up to form a dipole, and so on. And in the end, on an open chain, you are left with a free dipole, but physically separated. So it's like saying you have a Dirac string with one monopole on the moon and the other on Jupiter, whatever. And this is precisely the same, no matter how long or small is the chain. This is the fact of life. you have one end of, this is very similar to, spin-ons and whatever, I mean, different ways. So this is the reason why I even try to call them as dipole fractionalization. So Majoranas that arise here are basically nothing but manifestation of dipole fractionalization. Okay.
What is the definition of phi and psi, which is sigma x and sigma y?
That's right. This is a non-local relation. I can show you there is a transparency. Huh?
What is the definition of the spin expression?
It's there. I'll show you later. But let me continue with this. So this is a very well-known fact. I mean, I'm not inventing it. All of this is very well known. In fact, Leib, Schultz, Mattis could have easily claimed that they were the inventors of all this, but of course it took Alexei Kitaev to get the credit. But never mind, that's not our problem. My problem is, suppose if I have realized such a quantumizing model in whatever context, and my context is quantum optical situation, Rabi lattice problem, how would I detect such a mode? Now I looked carefully at all the important papers, basically two, the Leib's paper and the Feites paper, and I found something very nice. See, generally if you have a ordered phase, then for L sufficiently large but in the bulk, suppose you have two sides in the bulk, not at the end but sufficiently far away, then this correlation would have grown as p to the power 2, p square, because p is the spontaneous polarization. It's the expectation value of sigma x. So this is what we learn when we learn about orders, that if you are far away then it's just p square. That's how we define order parameter. But precisely because there are these localized Majorana fermion modes, and this is an exact answer, this is not something I'm making up, this is given in these papers. I mean, the result is given here, but the procedure is developed here. This exponent happens to be very unique and 8. It's not 2 or 2.5 or 3, it's just 8. And both of these are physical observables. P is what you measure in lab, spontaneous polarization. And in principle, I suppose people can invent some scheme to measure end-to-end correlation precisely. So, my proposition is that if you were to realize, suppose you had realized such a model problem, or there is a real material which is quantumizing exact or almost quasi-one-dimensional quantumizing problem, then all you have to do is measure spontaneous polarization, measure end-to-end correlation, and look at this plot. If it is there, you will just get a straight line. So these computed points are basically not for quantumizing model, they are for the full Rabi lattice, within of course some cutoff of number of bosons to be 4 or 5 on the per side. But these red dots are computed parametrically by varying one of the parameter, t in this case, the hopping. And you see that the points are pretty close to the ideal line. And so this is my suggestion, if you wish, or proposition, that this is one way of trying to assert that my system has realized Majorana modes or not. And this is very parameter independent case. I mean, no matter what my t was, no matter what my j was, and so on, it doesn't matter. You measure two quantities and you check if they have the right relation. If they have, then you have Majorana mode, as long as it's xy, quantumizing case.
What about if you choose one end point and another point in the bulk? How does it
This would still go as p square. It's a very precise relation end to end because of the localized wave function. I mean, the detail is given, but it's because both of the guys have certain localized nature of it. If one guy is inside, then of course you are in a, Then I also looked at the possibility of saying that whether it will survive if there is a tiny longitudinal field. Because as my friend Sujit pointed out, that these sigmas they behave like fermions only through some very highly non-local relations. So while the p-wave superconductor, which is given to be in the fermion language, is immune to local fluctuations or local changes, if I apply such local fields, why am I calling local? Because at every site I am just applying some finite amount of field. It could be random fluctuating electric field or whatever. Is this Majorana feature going to survive? So for that, of course, I do not have a precise analytical answer, though I have some analytical thoughts in mind which motivated me to believe that it will be there, at least for tiny amounts of eta, which means I cannot guarantee if the eta is very large, then of course things may change completely. This is all roughly. And then this is a computed curve. This is just for Ising quantum Ising model. If eta is 0, you have very good straight line. And if eta is little bit away from 1 but small, 0 but small, then you have basically in the strongly ordered phase, deep inside the ordered phase, you still have this relation being followed very nicely. Of course, near this end is near the transition point. Here you have large deviations. But deep inside the ordered phase, you are almost always guaranteed. In fact, this is not the best calculation one can do. I'm sure there are better experts than I am on DMRG. But even within my very simple calculation of DMRG, we have reasonable confidence that as long as eta is a small fluctuation or a small field, I believe experimentalists can find ways of shielding it, but let us say there is some small field. I'm saying it may not it may not completely kill the Majorana mode. And the reason is that as long as Majoranas are localized sufficiently, they will continue to behave as a Majorana. This is what Professor Shankar Das Sharma was alluding to in the last talk, that they may not be perfectly localized objects, but as long as they have a wave function which is sufficiently rapidly decaying, they will survive, the character will survive. So this is just the zoomed version of that. So let me just summarize. Arrays of Rabi quantum cavities exhibit quantum Ising dynamics of atomic dipoles, and this is rigorous in the strong coupling limit. This is unlike the Jaynes-Cummings lattice model, which emulates Bose-Hubbard type behavior due to polar electron number conservation, but here there is no such number conservation, so no U1 symmetry to be broken. So the physics is different. It provides a possible route to search for the Majorana fermion modes, and my proposition is look for such a relation. Thank you very much.
Okay, so thanks a lot, Brijesh, for a very interesting talk. Running a little late, so if there are some urgent questions, then we can take one or two questions, otherwise we'll go on to them.
The Jordan-Wigner transformation is not local.
So
does that make it dangerous for the topological? In other words, in those variables, does a physically local perturbation in the original variables become non-local?
So let me go to the next slide. And see, the point which Professor Steve Given is alluding to is that the relation between sigmas and the size or my fermion variables is highly non-local. And does that make a difference? Well, that makes a difference because that is the reason why this term immediately lifts the degeneracy. Otherwise, it would not have happened. But the question, in fact, this question I tried to get an answer from Adi when he was talking about Majorana fermions, that what is more important? Lifting of degeneracy, of course, he's there. Sorry, I was looking for you somewhere. The lifting of degeneracy or the localized character. My feeling is somehow, and I have some very heuristic ways of trying to justify it, that as long as I have some localized fermion, see, if I solve this problem, brute force on some computer, I will get lots of propagating modes. That is what makes my band. But as long as I get two modes which are sufficiently localized, even if their energies could be disturbed because of non-local relation, I'm home, in my opinion. And this is what my numerics seems to suggest. At least in this limit, nothing seems to change much. Okay, you can say this may not be very large system, somebody has to do more systematic numerics, but the trend is very encouraging. And the way I argue it is through this, improvisation upon the Jordan-Wigner transformation, which, see, usually this is, you can look up this appendix of this paper of mine. Usually, this transformation is very pathological as far as sigma x is concerned.